As you briefly mentioned, I am mostly working on like biologically inspired modeling some biological processes or systems, especially interested in like agent-based simulations, defining some agents and their interactions, and then see what kind of global patterns emerge, especially as a collection. Would it be possible to converge on some, let's say, intelligent behavior? But it is possible to model that, I think, in different systems, in different models. For example, it could be artificial neural networks, or a society of agents like animals or humans, let's say. And so I will discuss some of the recent research activities of what I was doing, but specifically discuss a bit more about this recent two works. One is about meta-control of social learning strategies. This is finding the trade-off between individual learning and social learning, and try to allow optimum learning as a population using these strategies. And the other one is just not published yet, but in the process, which is using social norm or evolution of social norms to encourage cooperation in groups of agents. Yeah, unfortunately, I will not discuss too much about biologically inspired artificial neural networks learning, but it is similar kind of ideas, but I will also briefly mention that. Before getting into this, I would like to briefly introduce my group. So basically, I am a member of Computational Intelligence Group in Vrije Universiteit, Amsterdam. And here we have 5 faculty members specializing in various topics. But one of the main overlap or common theme is evolutionary learning or lifetime learning, also application to real-world robotics. So for example, in terms of research, evolving and learning machines, we are interested in proposing, for example, evolutionary or lifetime learning processes to design these robots, not only, let's say, simulation in real life, but also we are interested in embodiment, like these robots should somehow interact with the real world. And also the body shapes, for example, we can 3D print them and then test how body shapes affect their, let's say, performance. And for example, here we have modular robotics platform. We can print these modules and then attach them with motors. And this is like distributed kind of controllers, different motors, different joints. And then the goal would be to optimize this robot to perform locomotion behavior, for instance, or different, perform different tasks like object avoidance, etc. So in addition to that, also we are interested in like multi-agent systems, collective behavior, especially properties like self-organization, emergence. And here also we also like cooperation, communication. So here also we have several platforms that we can test these algorithms. In terms of my research, I will mention just several research activities that I was doing. So more recently, which I will discuss a bit more detail, the social learning strategies. So the question here was to how to learn efficiently as a population. So here we are considering a population of individuals that can learn during their lifetime. And in nature, there is, for example, different strategies emerged for learning. Individual learning is one thing. For example, they can learn during their lifetime by trial and error. This is modeled as in systems, let's say, reinforcement learning. But also in nature, especially social living animals, social learning emerged or evolved. This is to reduce this learning cost, because every individual, if they learn during their lifetime, then there is this always exploration cost. So the social learning is helping to reduce this cost. Basically, the individuals can just copy the behavior of others. But it introduces other problems, although it is like sample efficient, which I will discuss in more detail on that. And here we just were looking at how to use these strategies to basically learn as a population. Using these strategies. And more recently, at the moment, I'm working on these social norms and social norm evolution. Here, the idea is that how can we, again, we have groups of lifetime learning agents, but the idea is if they are self-interested from the purely, let's say, rational agent theory point of view or reinforcement learning, everybody is interested in maximizing their own payoffs. But in this case, it's not possible to converge on a cooperation because the agents, if everybody's maximizing their own payoffs, it may not be the good, let's say, role distribution in this group. Some agents should do maybe other tasks. So here we are using social norms to encourage that behavior. And here, also from my previous work, especially during PhD, I was focusing on biologically inspired learning in artificial neural networks. Here, similarly, I was considering neural network as a collection of agents like neurons. And then the goal is how can we learn global learning or global behavior by these agent-based rules, agent-based changes that they can do in connections, for example, how they should change their connections. And here I was mainly optimize this behavior of these neurons on locally, finding some rules, how they should change their behavior to converge on a global learning pattern. And similarly, I worked on this Phoenix project, Fat Open project, and we did also try to build these sensor networks. These are like limited nodes with limited computation capabilities, but we had many. We have collection of those. And then we can deploy them in difficult to access environments, for example, underground, river or pipeline. And the idea is to use, again, a swarm idea where they can communicate with each other, collect different, let's say, sensors, data. And then at the end, when we extract them, the idea was to try to map the topology of the environment or find some properties, what the properties of the environments may be. And last but not least, I'm also working on evolutionary distributed learning. And in this case, the idea would be that we have, again, similarly decentralized distributed nodes. And then each node may be required to learn certain local function. And how they learn would be to communicate with each other, exchange some parameters, for example, in terms of their model. And overall, they need to solve some problem. For example, it could be detecting human presence in an environment, or in this case, it could be, for example, exchanging packages from different, let's say, from seed node to target node. And here the goal would be to optimize this communication protocol, but this optimization is local, so we don't have global optimization, but each node is doing this optimization itself in their location, and then the goal would be to solve this global problem somehow. So now, by the way, if you have any questions, just please feel free to interrupt. So now I will discuss in more detail these social learning strategies. Here, the idea was, as I briefly mentioned, how to learn efficiently as a population. We have certain strategies. Individual learning can improve the behavior, but involves this learning cost. So this could be trial and error cost. It should sometime try to see what other behaviors may be better because maybe there is some environment change. But there is a cost because of this opportunity cost, and also the things that they are trying may be expensive, like it can involve some danger, maybe so there will be some cost of doing that. And in nature, there is the social learning. Here is purely based on copying the behavior of others. So the idea is that they are exploiting the exploration performed by others. So in this case, there is no learning cost because it's just based on copying. And this is sample efficient. It's reducing the cost, but introduces other problems. So for example, when to copy. Social information can be less accurate because it's based on purely copying. If there's environment change, then if I still copy the behavior of others, then basically I cannot learn new behavior. And another very important, actually also discussed a lot in the literature, is who to copy from. So this is also very important to identify which individual has reliable knowledge, and then I would copy the behavior. And here in nature, especially, there are several strategies emerged and also explored in the literature. For example, it can be based on age because it can be indicator. It can be based on success, prestige. And in nature, especially, success is not very, possibly not very possible to measure, but there are different indirect indicators that can be used or can be used to basically have this bias for selection. And also another problem is if we have this social learning, then there is the information becomes public good. So when there is public good, there is always problem of rewriting. So since there is less cost, agents would select this behavior more because it's cost effective. But then they are free riding the exploration of others. Then if everybody does that, then there will not be any more exploration. In this case, there would, if the environment changes, for example, then the population will not be able to learn. Just they will copy the behavior of others, and this would be suboptimum. In this work, we looked at, we selected two strategies, individual learning plus these two social learning strategies. One is success-based. This is basically copying the most successful individual in the population. And the other one is conformist. This is copying the behavior that is performed by the majority of the individuals in the population. And here, the scheme or the model that we use, here we consider two separate populations. One population is individual learning and conformist learners, social learners. And the other one is individual learners with success-based learners. As I mentioned, the conformists basically just looking at what the behavior that is performed by majority and then copy that. And success-based is just looking at who gets the, for example, maximum reward and then copy that behavior. And here the task is multi-arm bandit. Here, for example, for two-armed bandit binary decision-making task, we have two options that have some reward distributions associated with them. When it's selected, it provides some reward. But the agents, of course, don't know that, but needs to figure out which action to select. And using this population information, as a population, they can converge on a, for example, should converge on a action that provides higher average reward. And yes, here it's a bit complicated. I mean, too much information perhaps, but we can just focus on two lines like red and black. So this is basically providing the showing the ratio in the population. How many individuals are individual learners? How many individuals are social learners? And social learners correspond to, in this case, we are looking at individual versus conformist social learners. And here the black line shows the individual learners ratio in the population, and then red showing the social learners, conformist social learners in the population, their ratio. So it's like, this is like from the evolutionary game theory of point of view, we just measure how many individuals in the population, depending on their fitness, their success, based on selecting which action to take, receiving these rewards. And basically there are two strategies competing in the population, and we show which strategy is prevailing over time through these generations. And this gives us insight which strategy is better in what environment. So for instance, here starting in the beginning, of course, they don't know which action to select. They randomly initialize, and they keep their own model which action to select. Basically, each action has certain value. This is very simple reinforcement learning, like greedy, epsilon greedy algorithm in terms of individual learners. And social learners, as I mentioned, just copy. There is no exploration. And here in the beginning of the process, individual learners are basically high in numbers, but after majority of the population learn the optimum behavior, then individual learners become costly because of this exploration cost. And since social learners don't have this cost, their number increases and they become dominant strategy in this population. And of course, individual learners do not go to zero because we have always some mutation rate. So some social learners have mutation to be individual learners. So basically we have this baseline due to this mutation rate. And here we also look at other aspect, which is what happens after environment change. Environment change here means that we swap the reward distributions. For example, the optimum distribution is not anymore the first action, but the second action. So basically just swap the reward distributions. And then here we see the response in terms of this environment change. Since the social learners are just copying the optimum behavior that was previously optimum in terms of environment change, they were still performing that. And after environment change, because of this, they drop in their numbers, and we see increase in individual learners until they again majority learns the optimum behavior, new optimum behavior or action. And then again, they become costly and reduce in numbers, and then social learners again become dominant in the population. So if we look at success-based, similarly, a similar plot, just in this case, individual versus success-based social learners. So here we see similar pattern in the beginning, but if there is environment change, then there is not too much response in terms of increase in the individual learners, because in this case, it is possible to just if there is only one individual learner in the population, then it may find the new optimum behavior, and then social learners directly copy that, and then it will spread very fast. Then we are not seeing this response due to that. But in terms of conformist, it takes more time to learn this new behavior, and then basically they increase their numbers. So this is basically showing, but we were thinking what would be the cases where this would not be true. So for example, you may think that it's always optimum just to use success-based learner. So the social learners should always use that, because whenever I have the best, let's say, behavior, then they just copy that. So we were thinking what would be the cases that would not be true. So one idea or hypothesis we had, that if we have uncertainty in finding out who is the successful individual in the population, then it would not be possible to basically learn this behavior because we don't know who is successful. So to test this hypothesis, we introduced this environment uncertainty. For instance, here I show the three separate populations. This is individual learners with success-based and individual learners with conformist. We always need individual learners in each population because otherwise there will not be exploration. But here I show the aggregated average reward in these populations, the learning process, when we have these different strategies. And the way that we introduce this uncertainty is basically we model these reward distributions using these Gaussians with certain mean average reward with certain standard deviation. And in case of low uncertainty, there is not overlap between these two distributions. So it is easy to figure out which reward is coming from which distribution, whether it's optimum or suboptimum. Here's optimum and suboptimum is based on the reward, the magnitude of reward that they provide. So basically higher optimum means the higher reward distribution on average. And higher uncertainty case is when there is this overlap between these distributions. So in this case, even though, for example, you may have high reward that is sampled from suboptimum distribution, it may not necessarily mean that it's coming from the optimum reward distribution. So it may be the case that it's coming from suboptimum reward distribution. Then if we copy that behavior, basically we are copying suboptimum behavior that would not be good for us. So this is basically what we tested. And based on that low uncertainty case, we see that the conformist strategy is taking a bit more time, but they converge on higher average reward as a population. For example, this is individual learners. The difference is due to this exploration rate, epsilon. And here, when we have high uncertainty, on the other hand, we see a completely different picture where success-based performs even worse than individual learning. This is due to the also copying the suboptimum distribution, basically the behavior that comes from suboptimum. But interestingly, conformist behavior is quite resilient to that. So basically it performs as there is no uncertainty in the environment. So we basically formalized that uncertainty. It is quite a simple idea, is basically what is the probability of sampling. So we sample, let's say, rewards from these two distributions, and what is the probability of sampling higher rewards from suboptimum distribution. So basically we find that probability. So this is nth order statistics. In the paper there is a formula for that, and given two distributions or many, it's possible to just find this uncertainty, and we call this uncertainty optimum distribution prediction uncertainty because of the uncertainty of predicting what optimum distribution is. And here, this is analytical probability calculation, depending on sigma 1, sigma 2, of course, also means. And also it depends how many samples that I generate from each of these distributions. For example, if I generate half and half, for example, 50-50, let's say I have this probability distribution or probability computation. And if I have more, if I'm sampling more from suboptimum, then of course there is higher probability of being deceived, or higher probability of getting higher rewards from suboptimum distribution. So here, basically, this is analysis of that. And here is showing the relationship between this prediction uncertainty in the environment, depending on this configuration, versus what is the difference between success-based and conformist strategies. So basically, the higher the probability of this, higher the uncertainty, the higher the difference between these strategies. So basically, this shows us that success-based fails if there is this uncertainty. And based on this analysis and trade-off, we came up with this hypothesis, which is this meta control. This is also inspired by the neuroscience. So in neuroscience, it is proposed that in brain, there are multiple strategies at the same time, competing with each other, depending on the environment. For example, one strategy may be chosen. And one example is model-based versus model-free learning. So there are quite large literature in showing that these strategies dependent on the environment uncertainty. And depending on that, brain or in animals, they can arbitrate between these strategies to basically increase the efficiency of learning. So here we mimic, or we did the similar thing on social learning context, where we have these different strategies, and depending on the environment, what kind of mixed strategy or like meta control strategy we should have that would provide us optimum learning, independent of the environment the agent is facing. So of course, there are two parameters of the environment in this case. One is environment change. For example, if there is environment change, then it's obviously we should switch to individual learning. And depending on the environment uncertainty, after the optimum behavior is learned, we should switch to social learning. But depending on the uncertainty, it could be either success-based or conformist. And here we basically modeled many different approaches to model that. So each of these models are basically meta control strategies that can switch between, arbitrate between these strategies depending on the environment or not. Some of them are fixed. Some of them are learned, for example, using genetic algorithms or neural networks. But some of them are rule-based. So basically, this is our definition. We defined agents that can identify somehow environment change, and then identify the uncertainty environment, then switch these strategies. And then here, I show the trade-offs between these different meta control strategies. And if we have only individual learning, we have, so this shows the performance, the average population reward after the learning process, and exploration cost. If we have only individual learning, then we have quite a lot of exploration cost. This is also a log scale. And other approaches, for example, the rule-based approach, and also the ones that I learned, for example, based on genetic algorithm, they converged on similar performance exploration trade-off, where the exploration is way much lower and performance is also higher. Yeah, this can have effect, for instance, in learning in multi-agent systems, where each agent would not need to learn themselves, so it would be very costly, but it is possible to just copy either parameters of the learning of other agents to reduce this learning cost. Yeah, so here another way of looking at it is similarly from the evolutionary game theory point of view. We have these different meta control strategies. So each of them can switch between these strategies in the environment. And here we tested, we put them, the agents now can perform switch between these strategies, these meta control strategies. And then we test what are their success relative to each other. So in the population, which individuals that use which strategies would dominate others. So these graphs basically looking into that. And we tested on different environments with volatile, low and high uncertainty, and also other environments in the paper, but I'm just showing two examples here. And volatile means that we change the environment very frequently. Here, for example, each change is indicated with these arrows. And after each change, the uncertainty of the environment, this reward distribution configurations, reward functions, the parameters are changed randomly. So here we see that if there is low uncertainty, there is still some strategies based on success base performs relatively well. But on the other hand, especially in high uncertainty case, the models, the meta control strategies that incorporate this environment uncertainty and switch accordingly performed the best and dominated others. So this is again the ratio in the population of these strategies through generations. And this shows, basically gives us the idea which is the most successful over time. So this is our conclusion about this work. Then I will just, 2 slides, I believe, discuss similar but a bit different work that I'm working at the moment. This concerns social norm evolution. So in this case, how we can learn the division of labor in self-interested lifetime learning agents. For example, the way that we model that, we have these agents. This is a group of agents, and each cell is encoding one type of role that can agent play in this group, and there is some neighborhood that they can interact with each other, and we defined a game to test if cooperation can emerge. So the game is that in this group, we would like to have certain role distribution emerge, like each agent should select certain roles to optimize the group average payoff. And we define this game. For instance, we have a cleaner that doesn't get any payoff, but it's beneficial for the group because it cleans if there is there is always constant waste accumulation in the environment, and if there is a cleaner in the environment, it cleans this waste in the neighborhood, and this helps the working of other agents. Otherwise, this waste accumulation over time reduces the fitness or reduces the payoff that the other agents receive. And also we have different roles. For example, forager can just forage and get 3 payoff each time. And we have hunter role that is dependent on also cooperation with other hunters. So it can only get higher payoff if there is more hunter in the environment. So basically they can cooperate and hunt maybe bigger prey. And we have also soldier role that is protecting the neighborhood. In this case, we have random adversarial attacks, we assume. And if there is soldier in the environment, in the neighborhood, then it can protect these adversarial attacks. If there is none, then randomly these agents, the payoff that the agents receive can be stolen. And based on this game, we test this, oops, sorry, I have something wrong. Okay, based on this game, we test these different approaches. So one would be, here, if you have only purely selfish learning, basically if each agent is maximizing their own payoff, so basically they all settle on forager because it's just gaining 3 payoff, and cooperation would be a bit more difficult in this case. Finding this configuration is a bit difficult, and nobody selects cleaner or soldier because they don't provide any payoff. On the other hand, when they do that, we have this learning process. This is time step versus average group payoff. In the case of selfish, we show in yellow, they basically, in the beginning, maybe they are receiving some good payoffs, but overall, after a certain time, this waste accumulation increases in the environment and there is no protection against adversarial attacks. Basically, they suffer from these 2 effects and they basically settle in a very sub-optimum payoff. On the other hand, if we have social sanctions, here we are using social norms. Social norms are basically like bottom-up, again, rules. Each agent can monitor their environment, and they can approve or disapprove the behavior of other agents through rewards and punishments. So this is what we are testing here. And in this case, we see this emergence of this pattern where there are these neighborhoods that each neighborhood, there is one cleaner that is taking care of the basically waste accumulation in the neighborhood, and there is the soldier that is taking care of guarding for the adversarial attacks. And we see that emergent pattern, and the rest is basically hunters, because having hunters in the environment provides the highest payoff. Then the learning process is basically this, I guess, pink or magenta, where it is much better than selfish agents. And also we tested different approaches. For example, without social sanctions. These are still, in the case of social sanctions, by the way, they are still self-interested, but they are guided by the social norms, how to behave. And in case of other approaches, for example, this was purely reinforcement learning, selfish optimizing their own reward, but it can be also altruist. So altruist means here they are not maximizing their own payoffs, but they are maximizing the payoff of their neighborhood on average. So in this case, we have this learning process. Still, I mean, we are not purely looking at how they compete each other, but still somehow lower than when we have social sanctions. And selfish altruists are half and half. Basically, they maximize their own payoffs and also the payoff of the neighborhood. Caring a little bit also in the neighborhood, then it is again sub-optimum. And centralized is basically there is no lifetime learning at all. What happens if we optimize this role distribution and define, let's say, in each cell, you should be this role, you should be that role. And if we do that, like optimize directly, it's like each agent has a specific duty genetically defined, in this case, in this population. Then we have upper bound, which is this is centralized approach. And this is just relative based on this game, the maximum payoff that can be achieved. So with that, I would like to conclude, and thank you very much for your attention and joining.